Hello everyone. In this video we will discuss about area under the curve and how to use integral calculus to calculate the area under a given curve. So let's get started. Let us assume we are measuring some quantity y by changing x. For example, x can be time and y can be velocity. We have measured y to be 1.5 when x is 1 and y is 3.5 when x is 5. If I join these 2 points with a straight line, I will have a linear curve. In this case, the mathematical function of the curve will be y is equal to 0.5x plus 1. Now we are interested in finding the area under this curve. Before we jump in and do the calculation, let us first try to understand what exactly does the area under a curve represent in the next section. In this section, I will try and explain what does the area under a curve represent. As you might know, area is a scalar quantity, so it has only magnitude. Similarly, the area under a curve represents the magnitude of the product of two quantities x and y. For example, if x is time in seconds and y is velocity in meter per second, then the product of velocity and the time between the two time interval will give us the distance covered by something between this time interval. So if we assume this graph as our velocity versus time graph, the area under the curve y is equal to 0.5x plus 1 represents the distance covered between 1 to 5 seconds. Alright, now let's dig a little deep. In this graph, when x is 1, we have y value as 1.5, and when x is 5, we have y as 3.5. We also have a function of a linear curve which we draw between these 2 points. The function of the curve implies that for every small change in the x, which will be represented by dx, the corresponding y value will be defined by the given function. So to find the value under the area of the curve, all we need to do is to just find the magnitude of the product of the function and the small change dx. To do this, we are going to use integrals. In the next section, I will be sharing some basic concepts behind this method of finding area under the curve using integrals, and then we will use integration to find out the magnitude of the area under this curve. So how to use integration to find an area? Integration is similar to summation. Imagine this rectangle 2D surface. This surface has an overall area of A. The height of the rectangle is given as a function of x. If we consider a small strip with thickness dx and height y as a function of x, the area of this small strip will be expressed as dA. Given all this, the small area of the strip dA will be equal to f of x times dx. If we consider the entire area to be sum of n number of strips, the area of the rectangular surface A will be expressed as summation of f of x times dx, while x ranges from 0 to n. By minimizing the width of the strip, we improve the accuracy of the result. So to do that, we shall introduce limit function and set the limit of dx to approach to 0. This summation expression with the limit function is called as limit of a sum. A limit of a sum can also be expressed with the definite integral of a function within the summation. So in this case we have a is equal to integral of f of x times dx between the limits 0 to n. Here 0 is the lower limit of the integral and n is the upper limit. So this equation implies that integrating the function between the limit 0 to 1 will give us the area of the rectangular surface A. Now let us apply this concept to the linear curve we saw before. Let us first define a small strip below the curve with thickness dx and with height y as a function of x. Assuming the strip to be rectangle with the area of dA, we have dA is equal to y of x times dx. Then the area integral of the linear curve will be a is equal to integral of y of x times dx between the intervals a and b. Here a and b are lower and upper limits respectively. So if I apply the area integral to the linear curve within the limits 1 to 5, I will have area is equal to integral of 0.5x plus 1 times dx between the limits 1 to 5. And solving this integral, we will get the area under the curve to be 6 units. In this way, we can simply use integral calculus to calculate the area under any given curve provided we know the function of the curve. This is a simple example with a linear curve, but this method will work for non-linear curves as well. I would encourage you all to try and solve this example of the velocity versus time curve. Here the curve is expressed by a quadratic function x square minus x minus 3 between the interval 4 to 6 seconds. Try to make an integral equation for the area under the curve with the intervals and solve it to find out the distance covered between 4 to 6 seconds. Please enter your results in the comment section for others to verify their answers. I will meet you all again in my next video. Bye bye.